Alright, so these rules are going to start to become pretty redundant. All we're doing is changing the type of equation that we're working with and the shape of the graph. The transformations are all identical. And now we're going to be working with a function called radical x. And we're going to perform the 3 reflections, 2 translations, and 2 dilations, just like we did with the previous 2 videos. What would happen if we had f of negative x? Well, that's asking me to plug in negative x into our function for x, so we have the absolute value, the square root of negative x. Now, yeah, I know you can't take the square root of a negative number, but you'll see when the shape of the graph, what if x is negative? Then you can take the square root of this number. So using function notation, I should recognize that this is a reflection over the y-axis, which means I can recognize by the equation, because x is becoming negative, it's a reflection over the y-axis. So the shape of the parent function, y equals radical x, looks like that. So if I'm going to reflect over the y-axis, I'm just going to look like that. Y equals radical negative x. And in this case, the domain, only negative numbers, so you can take the square root of a negative negative, which is a positive. So this graph does exist in the negative x quadrant. Let's now work with negative f of x. And using function notation, I should recognize that this is a reflection over the x-axis because the y values are changing signs. So the equation would look like this: negative radical x. So let's draw the shape of the parent function, y equals radical x. And now let's graph y equals negative radical x, which should be a reflection over the x-axis. That looks pretty familiar. If we go back to the quadratics function, we had the inverse graph looks like this. And the inverse graph was positive negative radical x. Well, this is both of the graphs combined. Positive negative radical x. And that should facilitate the inverse graph. So if we had a function called radical x, let's find f inverse of x. So the inverse graph, we're just going to have to do a little bit of manipulation here. Let's just do it graphically. We don't really necessarily even have to do the algebraic representation of the inverse. This is y equals radical x. So graphically, inverse is asking me to reflect over the line y equals x. So that graph would look like that. Now you may say, hold on, that's only half of the parabola. You're right. If we were to take the inverse of a quadratic, we would get something that looks like that. Now the problem with that is that the inverse of this quadratic, the radical function, is not a function at all. So to ensure that the inverse is a function, they kind of just say, let's get rid of this part, just to make sure radical x is a function. Just a little bit of side note, not important to know, but the reason why radical x is only the top portion is to make sure that the graph is a function. Do some translations now. Still working with radical x. And again, the point of all of these topics, whether it's quadratics, radicals, absolute values, is recognize what is inside of the function and what is outside of the function. And in this case, the function is calling for taking the square root of something. F of x minus 1, I could see that this x minus 1 is inside of the parentheses, which means we're manipulating an x value, which means we're moving horizontally. but we're going to move in the opposite direction. If it's -1 in the parentheses, we're moving right 1. And now we could recognize from its equation that we have an x minus 1 before we take the square root. So this will be a horizontal translation. Here is the graph of y equals radical x. This entire graph is going to be picked up and moved to the right 1 unit. So we're going to have that y equals radical x minus 1. Alright, how about a vertical translation? Well, f of x plus 3, I should recognize from function notation, and this is moving in a y direction up 3 units. But now, because of its equation, I should recognize that I'm adding 3 after I take the square root of something, so I'm moving in a y direction. Here is y equals radical x. So the graph of y equals radical x plus 3 is moving up 3 units. 2 dilations. Let's say we have 4 times f of x. Well, that'd be 4 times radical x. And just like quadratics and absolute values, this is going to make the graph more narrow. Y equals radical x. Let's just choose 2 ordered pairs in this graph and see what happens. The ordered pair 1, 1 lies on this graph, and the ordered pair 4, 2 lies on this graph. The reason I know that, plug in 1, the square root of 1, 1. Plug in 4, the square root of 4, 2. So now this is asking me to multiply my y values by 4. So if this is 1, 1, then we're going to have 1, 4. If this is 1, 4, then we're going to have 2. Let me try this again. If this is 4, 2, then we're going to have 4, 8. So here is the graph, and of course, 0, 0. When I multiply 0 by 0, I still get 0. Here is the graph of y equals 4 radical x. If we had f of x equals radical x, and what would be the effect on the graph if we multiply by a half? Well, that would be 1/2 radical x. And just like the previous 2 videos, this is making the graph more narrow, more wide. Y equals radical x. We use these same 3 ordered pairs. This is the ordered pair 1, 1. This is the ordered pair 4, 2. And I'm going to multiply the y values by half. Well, if I multiply 0, 0 by half, 0, 0. This y value, again, I'll write the ordered pair as 1, 1. If I multiply the y value by a half, I have 1, 1/2. If this is the ordered pair 4, 2, I'm going to multiply the y value by a half, so I'm going to have 4, 1. So now we could see the effect on the graph if we change the equation around, and the effect on the equation if we change the graph around.